Hello students, my name is Shashank Shekhar. So let us continue with the exercise of chemical kinetics. So question 11 says that the following results have been obtained during the kinetic study of the reaction. So we are given 4 sets of experiment, and for each of this we are given the initial rate of reaction and the concentration at that point. Now what we have to calculate, we have to determine the rate law and the rate constant for the reaction. So for this we have to write the individual rate expression for each of the sets of experiment. So if we know this is the rate law, let us assume that with respect to A, our order is X, and with respect to B, our order is Y. And R is the rate of reaction, K is the rate constant. Now if I write it for the first experiment, then it would be 6.0 into 10 to the power minus 3. K we have to determine. Concentration of A is 0.1. So this is raised to power X, this is raised to power Y. For second we can write it as 7.2 into 10 to the power minus 2 is equals to K 0.3 to the power X 0.2 to the power Y. After that 2.88 into 10 to the power minus 1 K 0.3 to the power X 0.4 to the power Y. At last we can write 2.40 into 10 to the power minus 2 K 0.4 X 0.1 Y. So we can write the rate expression for each of this in this fashion. And now let us take two such rate expressions in which one of the concentration is kept constant. So let us take this and this. So in this case you can see that the concentration of A has been kept constant 0.3, 0.3. So what we will do here is we will just equate both of this. So we can write K. So for if we have writing for this, we can write K is equals to, so since K will be constant for each of these, as K is not dependent upon concentration, it will be constant, therefore K will be equals to 7.2 into 10 to the power minus 2 divided by 0.3 to the power X 0.2 to the power Y. For this we can write K is equals to 2.88 into 10 to the power minus 1 divided by 0.3x 0.4y. Now this and this will be cancelled out. Further we can just evaluate it. So what we will get, so if we bring this, if you cross multiply it, okay, so I'm cross multiplying it here, that would give you 0.4x by 0.2x is equals to 2.88 into 10 to the power minus 1 divided by 7.2 into 10 to the power minus 2. Further we can take this in one bracket, raised to the power x. So this is nothing but multiplied by 4. Now we can just remove this 2 to the 4, that would give us 2 to the power x is equals to 4, or we can write it as 2 to the power 2. So now since both of the bases are equal, therefore exponents will also be equal. So x will be equals to 2. Hence we can say that with respect to A, the reaction is second order. Now what about with respect to B? For that we will take such, so this is 4, okay, so this is 4. We will take such rate expressions in which B concentration is kept constant. So for that we have this 1 and 4. So in 1 and 4 the concentration of B is kept constant, where A has been changed. Now if I write it for 1 and 4, So it is given. So if I write the value of k for 1, then it would be k is equals to 6 into 10 to the power minus 3, 6 into 10 to the power minus 3 divided by 0.1x and 0.1y. This will be equals to 2.40 into 10 to the power minus 2, 0.4x, 0.1y. Now this 0.1y and 0.1y will be cancelled out. I will bring this thing here. So it will give us 0.4 by 0.1 raised to the power x, and this will be 2.40 10 to the power minus 2 by 6 into 10 to the power minus 3. Now let us evaluate it further. If you remove this, you will get 10 to the power minus 3 and 6 4 are 24, and this will be cancelled, that is 4. Here this decimal will be gone, 4 to the power x. So if you just equate both of this, you will get x is equals to 1. So which means that with respect to a, it is second order, and with respect to b, it is first order. Sorry, opposite of that. So with respect to a, it is first order, basically we have seen it right now, and with respect to b, it is second order. Now what has been asked here in the question, so we have to determine the rate law. So rate law will be rate r is equals to a to the power 1 and b to the power 2 squared times. What about the rate constant? How will calculate rate constant? So let us take any of this equation. Suppose I am taking this equation, right? So we have written here k is equals to this much. Now if you put these values, so k will be equals to 6 into 10 to the power minus 3, 0.1 to the power 1, 0.1 to the power 2. So 10 to the power minus 3, that would give us 6 as our rate constant. Now let us see the solution. So first we have written the rate expression for each of this. Second, we have divided this, so we got x is equals to 1, that is for a. For b, we got this thing as 2, therefore k has a value of 6. Now if I ask you that what will be the unit of the rate constant, so the rate expression was in this way: rate is equals to k a to the power 1 b to the power 2. Now the unit of rate is simply mole per liter per second. K will be as it is. Concentration of A will be mole per liter, that is raised to the power 1. And concentration of B will also be mole per liter, that is raised to the power 2. Now this will be equals to, so if I write it separately in this fashion, we can write it, no problem. So this will be mole per liter raised to the power 3. So this will be cancelled out, we will get 2 here. This will be equals to mole to the power minus 2 L to the power 2 per second. Now I have told you in the previous class that the one with the positive power is written first, so liter square per mole square per second. So it is written here liter square per mole square per minute. So if you see here, it is I think per minute. You can see it is given in per minute. Okay, so it will be per minute. Next question. The reaction between A and B is first order reaction with respect to A and 0 with respect to B. So basically it has been written here that we have a rate. So if you write the rate will be equals to k a to the power how much? So it is first order, so a to the power 1 with respect to A, and with respect to B it is 0 order, so it will be 0. Now what is been asked, so we have to fill in the blanks here. Here we have to write the concentration of A. Okay, here we have to write the initial rate, and here we have to write the concentration of A. So how we will do it? So we will simply use this thing to find out all the blanks. So in this equation we have rate, we have given concentration and all, but in none of this experiment K is mentioned. So first we'll find out K. So for that we will take such experiment in which all of the things are mentioned. So for experiment 1 you can see that A concentration is given, B is given, and rate, initial rate is given. Therefore we can write it as rate, that is 2 into 10 to the power minus 2 K. A is raised to the power 1, the concentration of A is 0.1, so raised to the power 1. Now B has a concentration of 0, that would give you 2 into 10 to the power minus 2 by 0.1 or 0.2. So I have written in this way, so you can write it 0.2. So K is the value of K is 0.2. Now for second rate set of experiment we have to find the concentration of A. So how we will find it? So rate, it is given as 4 into 10 to the power minus 2. K we have find out, it is 0.2. Concentration of A is not given, we have to find it out. Concentration of B is 0.2, so it will be raised to the power 0, that would give you 1. Now if I write A concentration, then it would be 4 into 10 to the power minus 2 by 0.2. That would give us 0.2 again, because this will be 10 to the power 1, 2 2s are 4, that will be 0.2. Concentration of A will be mole per liter, 0.2 mole per liter. And what will be the unit of K here? So since it is a first order reaction, you can see very clearly, so it will be per second simply. This is for first second set of experiment. This is for which one? This is for second set of experiment. Now next, for third set of experiment, how you will write it? So basically rate is equals to, we have seen it, so rate is equals to, the rate is given as how much? The rate is not given, we have to find the rate actually. So rate will be equals to K. K value is 0.2, A value is 0.4 raised to the power 1, and B value is also 0.4 raised to the power 0. That would give us 0.08 or 8 into 10 to the power minus 2. So this will be our value for rate. This is 0.2. Next blank, it is 4. We are again we have to find the concentration of A. So this is for experiment 4. In this case, rate is given as 2 into 10 to the power minus 2. 0.2 is our rate constant. What is the concentration of A? We have to find. Concentration of B is given as 0.2, that is raised to the power 0. That would give us A is equals to 0.1. So if you calculate it, you will get it 0.1. Now let us see the solution. Let us see the solution. So from experiment 3, so what we have done from experiment 1, first we have found the value of K, that is 0.2. Now put these values for experiment 2 and we got the concentration of A as 0.2. Next we have find for experiment 3, it is 0.08, the rate of reaction, that is 8 into 10 to the power minus 2 mole per liter per minute. Now if I talk about the experiment 4, then it would give you A concentration as 0.1. Here I have said that the earlier 36 slide that it will be 0.2 per second. No, it will be 0.2 per minute, because we have this as per minute. Question number 13. So what does the question says? In this question we have to calculate the half-life for a first order reaction from the rate constant given below. So first of all, what is the rate law for the first order reaction? It is basically the rate is equals to, K is equals to 1 by T ln concentration of initial concentration of A by concentration of A at time t. So this is our rate law, integrated rate law. Now if I write it for half-life, therefore concentration of A at time t for half-life would be A naught by 2, and T will be equals to T half. Therefore K can be written as 1 by T half ln A naught by 2, sorry, A naught by A naught by 2. So we have substituted this value here. Not get confused, I have written it outside. Okay, yeah. Now this and this will be cancelled out, and we will get as K is equals to 1 by T half ln 1 by 2. This will be our final, so ln 2, it will go outside, and this will be our final value of K for a given T half. So we are given T half, so we are given basically rate constant value 200 second, 2 per minute, and 4 per year. Now if you want to calculate T half, so it would be basically T half will be K 1 by K, and the value of ln 2 is 0.693. okay, so 0.693 by K. Now for first, the value of K is given as 200 per second. Therefore T half will be 0.693 by 200 for first case. For second case, it is given as 2 minutes. So K is given as 2 per minute. It will give T half as 0.693 by 2. This will be second, this will be minute. And at last we have 4 year. So K is given as 4 per year. Therefore T half will be equals to 0.693 by 4 year. So you will solve all of this and get the value of T half for 3 different K. Let us see the solution. So basically it is 200, so that would give us 3.47 10 to the power minus 3 approximately. For minute it will be 0.35 minutes, and for years it is 0.173 minutes approximately. Question number 14. What does question number 14 says? It says that the half-life for a radioactive decay, so we have a radioactive decay, so the half-life is given as 5730. How much? Years. Now an archaeological artifact contain wood had only 80% of the 143 found in a estimate the age of the sample. So basically it is said that we have a radioactive decay of 14C and it has T half of this much. Also it is mentioned that the wood had only 80% of the 30C left. Okay, estimate the age, you have to calculate the age. So 80% is left. So suppose initially 100 would be there and now 80 is been left. So this will be our initial, isn't it, or A naught I would say, and this will be, this 80 will be our 80. Now we got the initial concentration, we got the final concentration. Now one very important thing, that for each radioactive decay is a first order reaction. Therefore we can calculate K from here. So we have just now seen the formula that K will be equals to 0.693 by 5730. Now from the integrated rate of reaction, T will be equals to 1 by K, that would be 5730 by 0.693 ln how much? A naught is 100 and by 80. This is nothing but simple calculation. You just calculate this and you will get your T. So let us see it. So first we have found this value of K, then we have substituted it 100 by 80 and we got 1845 years approximately. The experimental set of data for the decomposition of N2O5 2, this is N2O5, and this is the equation for decomposition in gas phase are given below. So this is our data that is given below. So it is basically 10 to the power 2 multiplied. So we are given the concentration, how the concentration is decreasing. So what we have to do, we have to plot a graph. We have to plot a graph N2O5. Then after we plot the graph, we have to find the half-life period for the reaction. Okay. So N2O5 versus T we have to plot. We have to find the half-life. We have to draw the graph between log N2O5 and T. Then what is the rate law we have to find and calculate the rate constant. And at last calculate the half-life period from K and compare it with 2. So let us solve it each of this one by one. First of all, we have given this N2O5 data, concentration of N2O5 and time. Both are given. We'll plot this simply. Then we will get this kind of graph. You can see that as the time is increasing, the concentration of N2O5 will decrease. It is very obvious. Now second, we have to find the half-life. So half-life is basically the concentration at when the concentration is half. So 1.6 by 1 by 2, that is 0.8. At this point, the time is 1600. So this is our half-life, 1600 seconds. So it is basically 1450. So it is written approximately. So we have taken 1.630, not 1600, it is 1.630 divided by half, that is 81.5, and 81.5 it has 1450 seconds. Next we have to plot the graph of T versus log N2O5. So when we plot, first we have to find log of this. So each of this log gives us this much. Okay, so when we plot this graph, we get this. Now if you see the first order reaction, integrated rate law, that it is written in this fashion. Okay, it is written in this fashion. If you just simplify this, we can write it as log A naught plus log AT, or we can write it as log AT is equals to how much? Log KT minus log A naught. If you compare it with the equation of a straight line, then this is y, this is mx, where m is k and x is time, and plus c is minus log a naught. Now what we have to find in this, we have to find we have to find our slope. So once we find the slope, we will get the value of k. So what is slope here? Before that, we will see that what is the intercept. So intercept is 1.8 minus 1.8, so that will be minus log a naught is equals to how much? Minus 1.8. Now if you find this a naught, that would give you 10 to the power 1.8. That is our concentration, initial concentration. Okay, so we got this thing, we got this. Now we will take any arbitrarity and we'll take that concentration at that time, and we calculate k from here. Okay, so first of all, therefore the rate law is this, since it is the first order reaction. Then we can find the slope in this way also. Again, the slope of the line is given by minus k.2303, therefore this much. So what it is being written here is that, so if you just see this equation here that I have given, it is basically ln, not log, it is basically ln, and it is minus here, sorry for that. Okay, yeah, plus minus here. Now this will be 2.303, so they have taken this t by 2.303 as a x-axis. Okay, k by 2.303 our slope, that would give us this. Next is the rate constant for a first order reaction is 16 per second. How much time it will take to reduce the initial concentration to 1/16th of the value? So what is being told here, that we have a first order reaction whose rate constant is 60 seconds. Now suppose that the initial concentration is A naught is X. So the final concentration will be 1/16th of the initial concentration. So the time is asked for this change. So 1/60 ln x by x by 16, that would give you t is equals to 1/16 60 ln 16. So you will calculate this, you will get your time. Hence 1/1/16. So they have taken the ln as 2.303 log. Therefore that will give you 4.6 into 10 to the power minus 10 approximately. During a nuclear explosion, one of the product is strontium and half-life of this is 2.881. If absorbed in the bones of a newly born baby instead of calcium, how much of it will be remained after 10 years and 60 years if it is not lost metabolically? So what is being asked here is that we have strontium as the product during nuclear explosion and its half-life is 28.1. Okay, it is 28.1. Now it has been also mentioned that it is absorbed in a newly born baby. So instead of calcium, it is said that in each gram we have approximately 0. Now question number 17. So it says that during nuclear explosion, one of the product is strontium. Okay, which has a half-life of 28.1 years. Now it is said that, so this is, sorry for this, this is 1 mu grams. Now 1 mu gram of this strontium, 90 strontium, was absorbed in the bones of a newly born baby instead of calcium. Okay, so how much of it will remain after 10 years and after 60 years? Very simple question. So T half is given basically. So K will be 0.693 by 28.1. So I have told you already that all radioactive reactions are first order. Now this much was absorbed. How much mass that is absorbed is 1 mu grams. So this is our initial concentration. Now we have to calculate the concentration at two different times. So T is equals to 10 and at T equals to 60. So you will use simply your first order integrated rate law, that is K is equals to 1 by T. So K is how much? 0.693 by 28.1 by T. T is 10 years for first case, ln, and the value of say initial concentration is 1 mu gram, and this we have to calculate. How will calculate this one? So ln mu grams is equals to 1 mu grams is equals to ln 80. Now if you multiply this on this side, you will get a 0.693 28.1 into 10. Now ln A by B can be written as ln A minus ln B. Therefore ln 1 mu gram, or I am writing it 1 only. So ln 1 minus ln 80. Now ln 1 has a value of 0. Okay, so that would give us minus ln 80 is equals to 0.693 by 28.1 into 10, or 80 is equals to e to the power minus. So if you evaluate this further, if it's 6.93 by 28.1. If you evaluate this, you will get it at time t is equals to 10. Now for time t is equals to 60, this will be replaced by 60. That would give you concentration of A at time 60. I'm writing it as 60 here instead of t, e to the power minus 0.693 into 60. divided by 28.1. That would give you concentration of A after 60 years. So we have done the same thing. We have taken it as this much. Okay, so it is 0.7814. So if you calculate it, you will get it 0.784 mu grams. And after 60 years, it is 0.278 mu grams. For a first order reaction, we have to show that for 99% completion, the time required for 99% completion is twice the time required for the completion of 90% of the reaction. So what we have to show here is that this is 2 times of 90. Now let us calculate this. So this is for a first order reaction. So if we write T99%, okay, so if 99% has been completed or consumed, then what is the concentration that is left? So suppose initially it was 100 gram. Now 99 is being consumed, so we are left with 1, isn't it? Similarly, this is for suppose 99. Now if I tell it for 90, then it will be 100 minus 90. 100 was initially, 90 is been consumed, so we are left with 10 here. Now if I write it T99%, then it will be 1 by K, okay, 1 by K ln 100 by 1, and for this one it would be T90% is equals to 1 by K ln 100 by 10, initial by final. Now if I calculate the value of K from here, then it would be T99% ln 100, and this will be T90%. So this and 10 will be cancelled, is equals to, sorry, K will be equals to 1 by T90% ln 10. Now let us equate both of these equations. So it will be equated, and T99%, 1 by T99% ln 100, I'm writing it ln 100 here. This will be equals to ln 10 by T90%. Now let us cross multiply this. So T90% is equals to T99% ln 100 by ln 10. Now ln 10 can be written as, ln 100 can be written as ln 10 to the power 2, and ln 8 raised to the power x is written as x ln a. So this was give us 2 ln 10. This ln 10 will be cancelled. Therefore, this will finally give us, okay, so something has been wrong here. So let us see. So we have the first order reaction. We have to show that 99% is twice the time required for the completion of 90 of the reaction. Now for that we have to write the rate law. In rate law, since this is the first order reaction, so for 99% we have to show this as, this is twice the time as T90. Okay, so percentage, yeah. Now next we will write the rate law for first order reaction for 99%. That will be equals to T99% by, okay, so first of all let us see, if 99% have been consumed, then what is left? That is 100 minus 99 is equals to 1. Therefore T99% will be equals to this much. Okay, now similarly for 90%, if you write it for 90%, then it will be 100 minus 90, that is 10. So 10 is left. Now coming back to the equation, we can write here it as T99% is equals to 1 by K ln, so since 100 is initially and finally we have 1, okay, for this case, and for this case it will be ln T90% is equals to 1 by K ln 100 by 10. Therefore K here will be T99 1 by T99% ln 100 Okay, and here it will be, okay, sorry, so it will be cancelled out. Okay, K will be equals to 1 by T90% into ln 10. Now let us write it on a different place. So it is basically ln 100 by T99%. Okay, ln 100 by T99% and 10 by T90. Now if you just multiply it, cross multiply it, then it would be T90 will be equals to ln 10 by 100. So this is the mistake we have done. So what we have done it opposite way. Okay, so we will write ln 10 here, and this you should remember, sorry. So what it would be finally, so we have done cross multiply wrongly. Okay, so we have done cross multiply wrongly. So ln 100 will be multiplied by ln 90% is equals to ln 10 multiplied by ln 99%. If I bring this here, so ln 99%, so T99%, not ln. T99%. So T 99% will be equals to ln 100 by ln 10 into T90. This would give us, so we can write from this here, ln 100 can be written as ln 10 to the power raised to the power 2, therefore 2 ln 10. So T99% is equals to 2 ln T90. So this was been asked to prove, so we have proved this. So we can see the solution. So T1 is this much for 99%, T2 is this much, so therefore it will be 2 times. After that, this question says the first order reaction takes 40 minutes for 30% decomposition. So it is being said here that we have a first order reaction, and it is said that at 40 minutes 30% of the decomposition has taken place. So initially suppose it was 100, then since 30% has been consumed, so 100 minus 30, that would give us 70. For T half, since it is first order reaction, for T half we have to calculate K. Okay, we have to calculate K here. Now K will be equals to 1 by T, that is 49 ln 100 by 70. Okay, so once you calculate this, it will be basically ln 10 minus ln 7. So once you calculate this, then T half is nothing but 0.693 divided by 49. Here it will be ln 10 by 7. So this will be our T half. So let us see the solution. So we have used this 100 by 100 minus 30, that would give us per minute. So unit is very important. So since it is a first order reaction, it will be per unit time, and you know that here it is given in minutes, so per minute. Now if we will just take 0.693 of this value, that would give us the T half. Last question. For the decomposition of azeoso-propane of to hexane nitrogen at 543 Kelvin, the following data are obtained. Now what we have to calculate here, we have to calculate the rate constant. So this is the time and this is the P total. So let us see the solution. So if you write, this is the equation. Okay, this is the equation for the given reaction. Now suppose initially the concentration is P naught and it is 0 and it is 0. So at time t, suppose P has been consumed, that would result in P this much and P this much. Okay. Further, what will be the P total? Therefore, P total will be this pressure, pressure of this plus pressure of this. That would give us P is equals to Pt minus P naught. So this will be the value of P. Now at time t, the concentration was P naught minus P. So if you put this value of P here, that would give us the pressure at time t, that is 2 P naught minus Pt. Now for a first order reaction, we know this thing, initial by final. Okay, so P naught minus P, that is 2 P naught minus Pt. Now P total was given, initial concentration we know. Okay, so hence we can calculate the value of K from here. So this was for today's class. We will continue the remaining question in the next class. Thank you.